use this to discuss what's 3-5 phase, what's 7 phase, what's 8 phase, or 9 phases. This can be some advanced topics, or 5 phases. It's been used in research and development. So this can be very advanced topics only in electrical engineering specialist area. Now, the balanced three-phase system. And it's very important to look at the word balanced three-phase system. Okay, now I told you the three-phase system. We have three wires, 3 conductors, and 1 neutral. But you need to just pay attention at the word balance. What does balance mean? You know your home is connected to single phase, right? Because your home is connected to phase A and the neutral, which will go to the transformer. That transformer will convert from 7.2 kilovolts to what? 120 or 240. Let me just show you this. We have 3 phases from the utility. Then it will be connected to the transformer. We have 3 transformers, 1, 2, 3. Each transformer will be for each phase, from 7.2 to 240 or 120. Then 240 or 120 will go to your home. So what's connected to your home is one of these transformers. Then your neighbor, let's assume this transformer on the left is transformer A, on the middle B, on the right C. So you are connected to transformer A, your neighbor B, your other neighbor C. Even though, let's assume that your home are identical, the same square feet, the same area, the same loads, but we cannot guarantee you will consume the same amount as your neighbor. So you might run on the dryer, the washer, while your neighbor maybe turn on the AC, the other one maybe is leaving the home, so the power is off. So this will make some mismatch, or something we call it unbalanced system, which means phase A consumption is not the same as phase B, is not the same as phase C. And this will create some problems into the electrical power utility when we have unbalanced or unequal load consumption. How can we avoid this? For overall large scale, they will try to supply an equal amount of loads to the same system. So I would say for this neighborhood, for a specific neighborhood, let's say for phase A, we're going to connect 10 homes, phase B, 10 homes, phase C, 10 homes. Then we will say like the overall average of phase A will be the same as overall average of phase B, the same overall average of phase C. So we are working based on average power that how they can consume. Then there is a small amount of percentage, unbalanced percentage can be allowed, up to 3%. Sometimes it can be violated up to 5%. If there is a 5% unbalance between this, more than 5%, then we need to take an action. So we can make some studies and say maybe phase C has lower loads than others, then we can connect additional home to make sure to maintain the balance. So again, overall thoughts to remove or to overcome some problems that we have in the power utility, we are trying our best to make it as balanced as possible. And again, balanced means identical loads, 3 identical loads. Phase A, phase B, phase C are identical. So as a result, when we discuss here in our analysis the 3-phase balanced system, we are going to assume these loads are identical. 3 identical loads. Okay? Then we can overcome all of these problems. The other thing, since we say it's balanced, we're going to assume the voltage of phase A, the same as the voltage of phase B, the same as voltage of phase C. All of them the same magnitudes. So, same voltage magnitudes. So the first condition for the balance, the first thing, 3 identical loads. The second thing, same voltage magnitudes for all 3 phases. For all 3 phases. Which means if phase A, if your home connected to 120, your neighbor must be 120, the other neighbor must be 120. And that's normal, that's what's supposed to be. The third thing, which is phase shift 120. This is a must, phase shifts 120. How we get it 120? It's basically 360 divided by 3, then it's 120 degrees. In other words, you are connecting at phase A with angle 0, 120 volts, angle 0. Your neighbor will be with 120 volts, angle negative 120. The other neighbor, 120 volts, angle positive 120. So when you have different angles, this will not impact the load. The load will run with any angle, there is no problem. But here, we put this angle, or choose this angle as 0, 120, negative 120 in purpose. Why? What's the point of using this phase shift? Why wouldn't use them as zeros and stop? You can imagine this as a vectors. You know, in physics or even in math, like this is vector A, and with angle 0, vector B with angle negative 120, vector C with positive 120. Okay? Let's assume this vector is like this, A, B, C. So imagine that there is an object in the middle at the origin, and assume all of these vectors, A, B, C, are equal in magnitude, while the angles are 120, 120, 120 between each one. What will be the net force? 0. Excellent. Why it will be 0? Because just try to push this way, this way, this way, this way. Or in other words, try to put in the calculator as 120 angle 0 degrees plus 120 angle negative 120 degrees plus 120 angle positive 120 degrees. And of course, the answer will be 0. Okay, what's the point of this? Why we do this? To get a 0 net. Where is the 0 net will be? This is the three-phase connection. We have phase A, B, C, and the neutral. What's the neutral current will be according to KCL? I neutral will be IA plus IB plus IC. And since it is balanced, it's going to be as I angle 0 degrees plus I angle negative 120 degrees plus I angle positive 120 degrees. Again, this yields to 0 amperes. Then, so we put this in purpose to let a 0 neutral currents. That's why we do it. So if we assume all of them are the same thing, if we assume all of them with angle 0, this means I angle 0 plus I angle 0 plus I angle 0. This here means 3 times I angle 0 degrees. What does this mean? 3 times the currents will be following in the neutral if we remove the phase shift, if we assume there is no phase shift. So this means the neutral current will be high, will be very large. And this means the conductor of the neutral cannot handle it. Because 3 times the currents will make the neutral heats, and this will affect the neutral, which is something that we don't want. Because high neutral currents, high I neutral is undesired. Therefore, we choose to have a phase shift so we can get something as 0 neutral currents. How can we take the benefits of this? This benefit will allow us to sometimes, since the neutral current is 0, let's remove the neutral. Why we need to use it? In some applications we can remove it. As we will discuss again, we will discuss this next lecture, but here just I'm telling you that we are trying our best to make the neutral current as low as possible. So I would say if the system is balanced, if 3-phase is balanced, so what will happen? I neutral will be 0. Okay? Now also keep in mind there are, how can we know it is balanced or conditions to be balanced? When we say balanced, there must be 3 things satisfied, which is 3 identical loads. Then We have same voltage magnitudes. Then we have 120 degrees phase shift. These three conditions must meet. When you read any statement, it says it is balanced. If you see any statement, is it balanced or not? Then you need to check these three conditions. 1, 2, 3. Those are the balanced conditions. That's how you test the system. Is it balanced or not? Okay? Does this make sense? Now, I mentioned the phase shift is 120 degrees. Is this correct? Okay. Now, how can I distribute this? Most likely, we will pick up phase A as a reference. As a reference with phase shifts 0. That's what we will do in three-phase system. We will assume phase A with phase shift 0. So here is phase A, phase shift is 0. So since the angle is 120, what's the phase B will be? Are we going to make it positive 120 or negative 120? Here is the concern. So we will say that we can have two options. We can have one option by saying that phase B will be negative 120, phase C will be positive 120. That's one option. The other option, by swapping this, phase A every time is reference. So we will say phase B positive 120, phase C negative 120, and all of them are in degrees. So we have two options. Which one is correct? Which one we are using in real life? Actually both. How can I distinguish which one that we are using? The first sequence is called positive sequence. Or in other words, ABC sequence. The other sequence is called negative sequence. Or in other words, it can be called ACB. So you need either to memorize this. Positive sequence ABC, negative sequence ACB, and how is the angles for each one? Because we're going to use this a lot. Not only in three-phase, we're going to use this in the motors, we're going to use this in the generators as well. Positive sequence or negative sequence. Every time phase A is 0, then negative sequence or positive sequence will determine the status. So, and remember, all of them are sharing the same magnitude. So let's look at the notes written here. We have positive sequence ABC, negative sequence ACB. So I prefer to use ACB, not CBA. I don't like ACBA, but whatever. How can I memorize this? By looking at the angle. You can imagine this. This is with angle 0. This is negative 120. This is positive 120. This is angle 0. This is negative 120. This is positive 120. Okay? ABC, ACB. Or in other words, you can imagine this in different way. Like, try to make this. So here is phase A. Since it's negative, here is phase B. Here is phase C. And here is phase A. Here is B. Here is C. Depending on the positive or negative sequence. So travel clockwise. Clockwise from A to B to C, right? This is positive sequence. From alphabets A, B, C. When you travel, even here clockwise, you will see A, C, B. Negative sequence. A, C, B. Let me write them as upper cases. Okay? Or in other words, in order to get the alphabets correct, you need to travel counterclockwise to get ABC. Right? So in other words, this means the top is the opposite than the bottom. Right? That's why the one is called positive, the other one is negative sequence. So the overall thoughts, again, just make sure the angle of phase A every time is 0, B negative 120, C positive 120 if it's positive. If it is negative, swap B and C. Then that's it. They are all sharing the same magnitude. So let me go back to this chart a little bit and just discuss some. These are the power lines, 3 power lines and 1 neutral. So depending on the currents and the voltages, we have 4 currents. Current of conductor A, current conductor B, current conductor C, neutral currents. Regarding to the voltages, since we have 1 neutral and all of them are positive, so we have positive, 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 and 1 negative, which is the neutral. So we have VAN between conductor A and the neutral, VBN conductor B and the neutral, VCN between conductor B, C and the neutral. Okay? So therefore, we are calling that we have 4 currents, 3 line to neutral voltages. Okay? We say this as line to neutral. Line to neutral. Voltage. Voltages, this means we have VAN, VBN, VCN. And don't forget bars. So that's the source from VBN, VAN, VBN, VCN. Live can be either A, B, C, can be any of A, B, C. Neutral is the negative returning currents, okay? Or returning, conductor. When we have 4 currents, 4 line, IA, IB, IC, then we have a neutral. Okay? Just look at this diagram, then you can get used to it. Now, how can we find the analysis? If it is balanced, again, this happens if and only if balanced, then you will see all of them sharing the same magnitude. But for positive sequence, it is, you see the sequence 0, negative 120, positive 120, negative sequence 0, positive 120, negative 120. Okay? Does this make sense? Here, just keep in mind, it is for balanced system. Now, how about the currents? Again, it is balanced system. So balanced 3-phase, this means all of the currents will be equal to each other. According to Ohm's law, I equal V over Z. Since Z is identical, this yields to the currents to be balanced. So IA, IB, IC, they are all will be equal to the same amount of currents. Then what will happen to the angles? We will not say phase A current will be 0. It will be with angle theta. We don't know. It might not be 0. We just assume the voltage is 0, not the current angle. The voltage angle is 0, not the current angle. So we put theta just in case what it is. Okay? Then what will happen to the others? Negative 120, positive 120. Other than that, the magnitude is the same. So when you do the calculation, you can calculate phase A, then phase B, just put negative 120, phase C, positive 120, if it is positive sequence. If it is negative sequence, just swap between A and B. Oh, sorry, B and C. Okay? That's how we do the formula. Again, they are all sharing the same magnitude, if and only if it is balanced. And for this course, we will assume every time it's balanced. Now, how can we convert this to time domain expression? We know for time domain expression, V, for example, in single phase, it is V RMS angle alpha. So we used to say V of t equals square root of 2 V RMS cosine omega t plus alpha, right? That's what we used to do in single phase. In 3-phase, the same way. So VAN cosine omega t, but there is no plus alpha because we used to assume the angle of VAN is 0.
Right.
Because VAN bar equal VRMS angle 0, right? That's we say cosine omega t plus 0. Okay? How about phase B? Just since it is positive sequence, I'm assuming it's positive sequence. Since positive sequence, A, B, C angle 0, A with angle 0, negative, B with angle negative 120, C with angle positive 120. That explains why we have angle negative 120 here, here angle positive 120 here. Other than that, they are the same. Just phase AN, VBN, VCN. How about the currents? The same way. Here again, we're assuming it's positive sequence. Therefore, for negative 120, we'll make this phase B negative 120. For C, positive 120. So we are repeating the same thing 3 times. But the thing which is keep into consideration, the phase shift. Again, here I'm assuming positive sequence. If it is negative sequence, it can be also something different. Okay, now there is something other than the voltages that we call it from line to neutral. There is other type of voltages called line to line. We used to say put the negative at phase B, phase neutral. That's what we used to do, right? Then we put one positive at A, one positive at B, one positive at C. That's what we used to do. Now there is another approach for the voltages. How? We can make the voltage between A and the neutral, B and the neutral, C and the, A and B, B and C. What do I mean by this? Assuming the voltage positive at A, negative at B. This is called VAB. Assume the positive at A, at B, the negative at C. This is called VBC. Assume the positive at C, negative at A. This is called VCA. So there's another definitions of the voltages by not using the neutrals. That's why it's called phase to phase, or sometimes we call it line to line. So here we will not using the neutral line. Don't use the neutral. By not using the neutral. So how we can do the calculation? VAB equal VAN minus VBN. VBC equal VBN minus VCN. VCA will be VCN minus VAN. We will discuss more details about this, but this is the live to neutral. Next thing we will talk about the balance formulas about it. Next lecture. And